We've now covered how to plan a VFR flight on a small aircraft between two small airports. That's really not what we want to be doing though. We want to be doing the big stuff. So let's have a look at IFR. Hi, I'm Grant and welcome to the 6th class in the flight planning series. Today we're going to be taking a look at the basics of how IFR flights are planned using this beast of a thing. This is the Jeppesen Airway Manual. You should have a copy of this if you're planning on sitting the flight planning exam anytime soon. And yeah, look at it, it's massive. There's so many charts and graphs in here, it's going to be impossible for me to cover everything that's in here. So this is just going to be a little introduction, a little bit of a flavor of how this thing works. I'd encourage you to go and look at this in your own time. It might not be the most thrilling bedtime story, but it'll certainly help you out when it comes to exam time. We fly under IFR, Instrument Flight Rules, because it opens up a lot more possibilities in terms of routes we can actually fly. Under IFR, we don't need to keep visual contact with the ground or navigate using the ground, allowing us to fly higher, faster, more efficiently over the oceans, and most importantly, in poor weather conditions. When you get to an airline, almost 100% of the flying you will be doing is using IFR, even if it's a beautiful blue sky day. And when we fly under IFR, we fly along a set route known as an airway. We can change from one airway to another airway at certain points to find the most efficient route from one airport to another. Airways in the past used to be all defined from ground-based nav aids like VORs or NDBs. And to get to the next ground-based nav aid, you would follow an airway. This limited the number of routes available because it was dependent on how many ground nav aids were available. So someone came up with the idea of developing waypoints that were defined from these nav aids. For example, if we had this VOR over here, we could define a waypoint called class, which is on the 180 radial at 10 nautical miles out. We could then use a flight navigation computer or a navigator using charts like it was back in the day to accurately fly from one point, such as this NDB, up to this new waypoint class. This new process of navigation was called area navigation, confusingly shortened to RNAV, which is the shorthand for radio navigation when you're studying for your ATPLs. But yeah, in this case, it stands for area navigation. The next iteration of RNAV came about when GPS became more prominent and we could define waypoints just from their latitude and longitude coordinates, allowing us to add in waypoints wherever we wanted basically. So we could create this new airway which goes a mixture of ground-based nav aids, points that are defined from ground-based nav aids, and GPS coordinates. Nowadays, commercial aircraft are fitted with a database of these waypoints, which are a combination of all these things, and the database is periodically updated to keep it up to date with all the new routes and waypoints, as well as the airways between them. In this class, we're going to have a look at some of the charts and get a feel for how IFR flights are planned using the Jeppesen Student Airways Manual. I haven't looked at these charts since I studied flight planning myself because they are not suitable for use today. They're all out of date. And there's a ridiculous number of charts in that book. So half the battle of the exam is just finding the correct chart. So getting familiar with it is very important. And I suppose the reason there's so many is just to simulate what it would be like to go through paper charts in a plane and make sure you have the correct ones. Nowadays though, you will almost certainly be using an iPad or some other tablet for your charts because it's a lot more lightweight and a lot easier to handle. So if we first take a look at some of the en route charts, I can show you more details about those airways we just talked about. So right before you get started on looking at these charts, right at the start of that big manual, there's a big introduction section which will explain all the acronyms, the symbols, the charts, everything like that. So it's worth having a look at that if you're ever confused or before you even start looking at these things. So for en route charts, there's high altitude and low altitude ones. So make sure you get the right one that's relevant for the question you're doing in the exam or in a question bank or something like that. So let's have a look at a low level one as example. The first thing you're going to notice about this chart probably is that it is busy. There's a lot going on here, but it's not as bad as it seems. Firstly, you only look at the bit you need. So let's say we're going to fly from Dublin over here to Manchester. So we'd fold up the chart to look at only this section here that we're actually flying to, and then we'll look for an airway that's nearby that goes from somewhere nearby Dublin Airport, such as the Dublin VOR, towards the area of Manchester. And the best one to do that is probably this one here, the Lima 975, if you can see that there. That goes along towards the area of Manchester in a straight line, nice and easy. You might be thinking, why are we not going all the way to the Manchester area? We're just going to stop at this place, Wallasey, or maybe before. Well, this is because after we've completed our en route portion of the airway, we fly a standard terminal arrival procedure to leave this airway and fly down towards the airport. And we'll have a look at that after we've done a bit of information about the airways. So let's just go along the airway and I'll talk about some of the points that are on it. So first we have the symbol over here in Dublin for the VOR DME, and the radial that this initial portion of the airway is based off is 097 degrees. And that is a magnetic direction. All directions that come off of ground-based nav aids are magnetic. Then we have this figure here, this 114, which is the length of this portion of the airway from this nav aid to the next one. So if you took up a ruler and measured and went down to the scale from the Dublin VOR all the way to the Wallasey VOR, it would be 114 nautical miles. The white writing on the black square, the negative writing, is the name of the airway. Above it we see 29, which is the length of this section of airway between two waypoints, in this case from the Dublin VOR DME to this point, Liffey. Why not to this point, Kisha? Well, our airway doesn't include this waypoint. You can see that by the fact that it doesn't go through Kisha, but sort of just loops around it, just as a curve around it. In reality, we wouldn't actually weave to avoid it, but this is just a graphical representation that says that waypoint is not included in this airway. Below the airway designator, we have a red number that says 5,000. This is our minimum en route altitude. Put simply, the MEA is the lowest altitude to be flown in an airspace so that it assures good reception of nav aids necessary to navigate along the route. It ensures two-way communication with the air traffic control, safe clearance from any obstacles within that sector, and it conforms with any air traffic control procedures that apply within that little sector. There's a lot of other versions of minimum altitudes that can be displayed here, such as minimum obstacle clearance altitude, or MOCA, which has a little T after it. If you have a look in the front introduction section that I talked about of the big folder, all the acronyms are there, and actually there's a great practical labeled diagram explaining most of this stuff. I think it's some like Morocco or something, I can't remember from the top of my head, but it shows you all these numbers and examples of what these numbers are and things like that. So if we look at the airway, we can see that our MEA, our minimum en route altitude, actually rises as we go along. It goes from 5,000 to 130 to 150, back to 13090, etc. So that means we're going to have to climb and descend on this route to stay safe and maintain air traffic control communication and stuff like that. So after that 5,000 point, we've got the Lima 975, but this time with a little arrow. This just means that this is a unidirectional airway. So from this point, Liffey, we can only travel from the west to the east on this airway all the way along. But in that section there, we would be able to go both directions. So you might have remembered from the previous airway that we weren't actually going to fly all the way to the MCT Manchester VOR, which is located here. We only flew to the Wallasey VOR, which is located here. Well, why didn't we go all the way to Manchester? Well, I know through personal experience that there's a group of stars in Manchester that start from this point here, which is Malad, which was along our airway. So you would fly to Malad and then get onto a star, a standard terminal arrival that would take you down towards the Manchester area, and from that point you'd fly an arrival procedure to land into Manchester. If you didn't know that there was arrivals that started from that point Malad that happened to be on your airway, what you could do is you could look at an airport star section and see if you can find a waypoint that starts from the suitable direction that you're coming from. We were coming from the west, so Malad makes sense. And then you could plan to fly along an airway that ends up or crosses over that point so that you can arrive using one of their standard arrivals and make it easier. This type of chart is called a Lido chart, which is what we use in my company, but you're not going to have a Lido chart in the exam, you're going to have a Jeppesen chart. So we'll have a quick look at one of the Jeppesen charts that's in that manual. We're going to have a little look at Alicante in Spain. The section for Alicante has a lot of charts and information in it that you would use in real life, such as operational details for run-up tests and low visibility procedures, but that stuff isn't relevant to us just now, so let's just have a look at the star, and one of these stars that we might use to arrive from the north. The chart I've picked is the Alicante star 10-2B, which shows the arrivals for runway 10 and runway 28. So let's just have a look at some of the main points of this chart. First of all, at the top left, we have the airport codes. Then we have an effective date, which is here. This one being the 18th of August 2017. And when you're flying two pilot operations, you will compare your dates to make sure that you both are using the same chart and that one of you isn't using an old, out-of-date one. There will normally be an index containing the current effective dates of these charts, and you would just refer to that to make sure you're got the most up-to-date one, the one with the most relevant information. Then we have a chart number, 10 meaning SID/star, standard instrument departure, standard terminal arrival, and then the procedures run from 2A to 2J in this case. If the leading number is an 11, so instead of 10 it's 11, it will be an ILS chart, and if it's 13, it will refer to a VOR approach. This is probably not going to be asked in any exam, but this is just to help you find the charts easier. So if it asks about an ILS procedure, search for 11. If it asks about SID or star, search for a 10. Then if we start to come down the page, we can just see general information such as the ATIS frequency, the airport elevation, and altimeter setting procedures. Then we have the actual meat of the chart, the important stuff about what the star actually looks like. Just slide that up slightly. There you go. So today we're going to pick the Valencia to Lima arrival to take us down to runway 10. This will be very useful if we'd flown an airway that took us as far as the Valencia VOR, for example, which is probably pretty common. If you flew an airway that went over the Calles VOR, then it would be better off flying the Calles to Lima or the Calles to November, 1 Lima to November, sorry, to arrive down in towards the Alicante area. So you pick a star based on which airway you've just come off or you're wanting to leave. Then we see some notes just below about the speed. So we've got max 250 knots at or below flight level 100, that's quite a standard thing, and max 220 knots when leaving the IAF, which is the initial approach fix, which is where these procedures should end, because this is the arrival section and then we move on to the approach section. So the initial approach fix being like a location, is obviously going to be where this ends and we transition into the approach phase of the flight. That's the point in a star. It delivers us to an initial approach fix we can then make an approach from. Then onto the diagram, we can see a lot of similarities in terms of the symbols from the en route charts. For example, on this leg, we'd see 196 is the direction. We've got a 59 nautical mile stretch from the Valencia VOR to Vilna. We've got an altitude of flight level 80 that we need to maintain, and VLC to Lima is the designator for the arrival that we want to do. Then down below Vilna, we can see a circle with various minimum altitudes. We've got 6,900 for this section here, 3,000, 3,500, 5,900 for example. And we wouldn't want to descend below these altitudes unless we're on a defined approach procedure under IFR conditions, or unless ATC are giving us radar vectors, which means they have our position and height on radar and are keeping us clear of all the terrain in the area. As I said at the start, there's a great section towards the back of that introduction section with one of these charts broken down into a lot more detail, and I encourage you to have a look at that for more information. SIDS, standard instrument departures, are very similar to stars, just sort of in reverse. So I'm not going to cover them, but again, encourage you, have a look in the student route manual, get familiar with everything. So after you've flown the standard terminal arrival, you'd move on to the approach plate. This one that we're going to look at is the ILS Zulu for runway 10 or the localizer Alpha for Alicante. This is the one that we would fly after flying that Valencia to Lima star. And you can see the first point is Vilna. That's our initial approach fix, which was the last point in that arrival plate. Initially, you can see that this is a lot busier than the arrival chart. This is because we are closer to the train and descending below the minimum safe altitude while on this procedure. So more information regarding the vertical profile is going to be given to us. Up at the top, we have all the general information about the chart. We have a few boxes with frequencies that we would have to speak to in the order that they're laid out generally. So we'd listen to the ATIS, then we'd speak to approach, then we'd speak to tower, then we'd speak to the ground control to help us taxi. Down below that section, we have general information about the ILS, the instrument landing system in general. So over to the right, we have an MSA ring that will match the one that we saw on that star diagram with the minimum altitudes for each sector. Below that, we have the missed approach procedure, which is what we would do if we're unhappy about the landing. Maybe the wind is outside of limits, maybe ATC have put us too close to the aircraft ahead, and they're still on the runway when we want to land. Maybe we've messed up and don't have an aircraft that is stable. There's loads of reason to go around, but basically this is the procedure that we would follow. And we can also see it in the diagram or down here, the initial part. We follow 100 degrees out to 3 miles from the ALT. Then we turn right to pick up the 126 radial out to Magal, which would be down here. We'd also climb to 4,000 feet and hold there. Below that section, we have a small list of notes, basically regarding the altimeter setting procedures and what to expect from the air traffic controllers. Below that, we have the diagram. That's basically the top-down view, the plan view of the approach from Vilna to the ILS to the runway. We can see various spot heights of terrain, along with the line that we're going to follow with the minimum altitudes, the ILS information again, with the Morse code identifier below it. You can just see ... And this is because you have to tune up a radio beacon and you can listen to another signal that comes from it in Morse code to make sure you're tuned to the correct one. So you'd tune up IAT frequency, which is 110.3. Then you'd switch on a little audio selector and you hear beep, 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 and that would make sure that you are tuned to the correct frequency for this ILS and this arrival. We can also see distances from various points on the approach from either the ALT VOR or the IAT ILS itself. So you can see that the ALT VOR and the IAT ILS are slightly offset. 5.5 miles on the ILS is 6 miles on the VOR, for example. Below this plan view is a side profile view of the final part of the approach, which really makes this chart different from stars and SIDS. We can see it covers the section from about 17.6 miles on the ILS to the runway, which is the section here on the plan view. This gives us a vertical profile to follow so that we can eventually meet the sloped cone shape, which is the ILS itself. So we can descend down to 4,200 feet until 14.6 miles. Then it's 3,300 and so on and so on. And on here you see 3,100 below with a dotted line. And I believe that represents a local section minimum descent altitude. So it's like a very localized MSA for this section. They could, in theory, descend you down to 3,100 and 2,100 if you needed to get your speed back or something like that. That means that you wouldn't intercept the ILS at the normal 9.5 mile point here, but you'd actually intercept at about 5.5 miles, which is quite a short final. but it's just there as a sort of a backup. They can do that if they want to. Below that side profile, we have a recommended vertical speed based off the ground speed your aircraft is. A good rule of thumb for a 3-degree standard glide slope is speed times 5 equals vertical speed. So say we had a ground speed of 120 knots, this little column here, 120 times 5 is 600, and you can see that they recommend a vertical speed of 637. So it's not exact, but it's quite a good estimation. To the right of that, we have information on the lighting system, which you can read all about in that introduction section, and the initial part of the missed approach procedure. The lighting is important when we talk about low visibility stuff. You need a certain amount of lights to be able to do low visibility stuff, and if certain lights have failed, that means that your ability to fly that might be a bit more restrictive. You might not be able to go to quite low visibility, quite as low on the descent before needing to become visual and doing a go around. Below that, in this section down here, I'll just slide this up slightly so you can see a bit better. We have a section on minimum descent altitudes or decision altitudes, which are dependent on your aircraft approach category, which is based on how fast you would fly this approach. A is basically for small single engine aircraft, up to D, which would be for big commercial airliners. So let's say we're category C, A, B, C, D. That means that we have to have an RVR with full lighting of 600 meters. The RVR stands for runway visual range, and this is a measure of how see-through the air is and how far horizontally you'd be able to see. And you can also see our minimum descent altitude here, or our decision altitude for category C would be 412, 412 feet. To the right of this section, you can see the option of a circle to land minima and a circle to land procedure. Circling to land is where you use the approach and for one runway, then circle round like a general circuit pattern to land on the other runway. You might do this if equipment was broken, for instance. So say for instance we wanted to land on runway 28, but the approach equipment was broken. We could come down the ILS for runway 10, and then at 1,240 feet, as long as availability is above 2,400 meters, we could break off to the right, circle round to the south, and land on runway 28 in a visual maneuver. Again, I would encourage you to go back to the introduction section, have a look at this, and just get familiar with the chart in general, because there is quite a lot going on this chart, but there's a good amount of repetition. You can see the missed approach procedure is said here, it's displayed here, it's also sort of said here a little bit. It's just loads and loads of information, loads of forms of that information to make you understand it as easily as possible. So after you've flown that approach procedure and you've landed on the runway, the next thing you want to have a look at is the ground chart. Again, I'm just going to use Alicante because that's what we've just been focused on this whole time. So these are fairly straightforward compared to the stars, SIDS and approach charts. This is because they're basically just a 2D map of the airport. We have some frequencies up the top, then the layout of the airport, information about the runway and lighting systems and things like this, as well as a few hotspots to be aware of. And again, we have some takeoff limitations. So you need a certain amount of visibility to depart this aircraft. And again, it's based on your approach category, which might seem a bit strange, but it's just a general good rule. So you see our aircraft category C would have to have 125 meters of visibility to be able to depart this aircraft safely. And all of the other columns refer to if certain lighting systems are not working, then the limit goes up. We need to be able to see further. On the flip side of this chart, we have the parking chart, which basically shows a more zoomed in version of the terminal building with various parking positions and their coordinates. So you taxi in and they'd say, I'll follow taxiway Charlie in to park on stand 21. And then you would be able to know where you're going, and there'd be various signs in the airport. You would turn left on Charlie and go up. Right on Charlie, then right again onto stand 21 up there. So that was a basic overview of what the Jeppesen charts look like and how you would go about using them. Remember, there's a key in the front. Introduction section is such a big help in this big fat manual that is the airway manual. Have a look at it, get familiar with it. It's all about just looking at the stuff a lot, I'm afraid. That's the only way to really learn it. So the next thing you do is want to create sort of a journey log, a navigation log with all your various points and relevant things on it to keep track of during your flight. I have an example of that here. This is a real flight plan that I got given by the flight planning department. So thankfully I haven't had to trawl through all the charts to create this thing. So this is the 4th page of our navigation log. We've already done a lot of navigating before this, but I thought this was best because I have a chart in the student folder which will match this section of a flight. We'll try and match some of the points to this chart so you can see how the chart info is transferred onto this journey log. So here you go, here's the section of the chart that we'd be looking at. This chart's absolutely massive, but you would just fold it up to the section that you need. And our first point that we're going to look at is here, Gotna. Gotna on the chart is located here. And from Gotna, we travel 044 for 23 miles to reach Blaka. The layout of your navigation log might be slightly different, but for our one that we use in my company, you have the magnetic heading or track here. And you have the distance from one waypoint to the next here. This is your distance to go. So if we look at Gotna to Blaka, Gotna 043 for 23 miles takes us to Blaka. Gotna here, 044 for 23 miles to Blaka takes us here. Again, just this chart's out of date. This will be a little bit more up to date, so the figures and the rounding might be slightly different. Then after Blaka, we continue following Papa 600 Airway on 029 for 50 miles to get to Tunso. So from Blaka, we're following the Papa 600 Airway for 15 miles on a heading of, a track of 028, and that takes us to Tunso. And you'd build your navigation log based off of looking at your chart, picking out the points you want to fly to. So we go Tunso, and then after that we're going over to Tala, which is over here. So that wouldn't be along an airway, that would be what you'd call a direct routing. So you don't always have to fly on the airways. Sometimes you get given direct routings if there's air traffic control capability to track you and make sure you're going the right direction. So after Tunso, after Tunso, we're going direct to Tala, and then we start an arrival into Edinburgh. Your journey log, as I say, might be slightly different, but just for interest, my one, it gives you the waypoint along with its coordinates. The routing that you're doing between the next waypoint would be, for example, Blaka to Tunso, you're following Papa 600 Airway. We've got the distance, the magnetic track, the true track, the time it would take, as well as the total time, the flight level you're expected to be at, the wind that is expected at that flight level. So we're expecting a wind from direction of 291 at 45 knots. The temperature, -11. The Mach number we're expected to be at, this isn't 619 Mach, 0.619. And then we have our true airspeed and our ground speed predictions. We also then have a fuel section here, and this is where we would track our fuel. We don't have to do it all the time, we just have to take periodic checks to make sure that the engines are burning the correct amount of fuel. We don't have any fuel leaks. So we might be 3.9 here, which is good, we've got 200 extra kilos. And then the two figures basically represent our contingency. So contingency, that extra fuel that you put on board just in case of any unpredicted and unforecast variations to your flight plan. If we've not used that contingency, we'd expect to have 600 more. And if we start to use it, we start to eat into this contingency. That's what these figures mean. So that's that. I'd recommend maybe planning a fictional flight between two airports, look at all the points you need, try and create some sort of nav log with the relevant points that you think you might need. So obviously the waypoints, the airway in between them, any altitudes that you might have to be between them, the directions in terms of magnetic and true. Remember, on the chart, everything is going to be a true direction, so you might have to convert it to magnetic. That'll be why those values were slightly different actually, now that I think about it. And yeah, just get familiar with everything, plan it out, and that should be good for your learning and your understanding.